All right, so this is going to be a video on implicit differentiation. So I'm going to start out by just talking about the differences between explicit differentiation and implicit differentiation, because up until the point where we've reached implicit differentiation, everything that we've been doing has been explicit differentiation. So we were given y as a function of x, or f of x, if you will, and we would find either f prime of x or y prime explicitly from that initial definition of the function. And so what would happen is after you do the differentiation, the y prime would just explicitly be stated. But sometimes that's not true if the relation between y and x isn't a direct f of x function. And so I can show you what that is in a second, but I'm going to talk a little bit about what implicit differentiation is. And it's basically the differentiation of each of the terms in a relation where y and x are not explicitly related to each other. And so in the relation between y and x, if it's not explicit, we'll find it implicitly. And so I have a couple of examples here just to sort of show you what implicit differentiation looks like. So for the case, this first one here, where we have y times x equals 0, this function isn't explicitly stated as y in terms of x. It has both y and it has both x in it. But if we're looking at it, y and x are related in such a way that it's not explicit. And so when we do the differentiation, we're still able to do the differentiation with regards to x, but we're going to get out a result that's slightly different than just the normal explicit differentiation. And so when we do this, we're actually taking the derivative of y times x, and we're considering y as a function of x. And so we have to consider that when we're taking the derivative of y, it's going to be dy over dx, or y prime, for that term. And so when we do the derivative of y times x here, we're going to end up with two terms from the product rule, which are going to give us the dy dx, or the y prime here, times the x as a separate term. And then we have to add the term where y is left alone, and we take the derivative of x. But if we take the derivative of x, that's just going to be dx over dx, or 1. And so we end up with multiplying y times 1 for the second term over here. And that just gives us y. And this is all still going to be equal to 0, since if we took the derivative of 0, we would just get 0 back out again. So we then are going to try and isolate the y prime by itself. So we can try and find what the derivative of y would look like. And that means that we take this term, this y prime times x term, and bring it over to its own side, and then bring the y term that was over here over to the other side. And so that gives us y prime times x equals negative x, or equals negative y, sorry. Make sure I say that right for you guys. And so if we have this relation between y prime, x, and y, then we're able to solve for y prime, where y prime is equal to negative y over x. And we just divided both sides by x to get this. And so this relation tells us what the derivative of y would look like given what the y value is and what the x value is. And so anytime that you have this relation here, you have to take into account both the x and the y in order to figure out what the slope would be. So this isn't exactly a function in terms of one variable. You end up looking at it in terms of a function of two variables. And this can start getting into something a little bit more complicated, which is called multivariable calculus. But implicit differentiation can still be thought of as just y in terms of f of x type of thing, and then just consider it just a basic calculus from there. And so we're still able to teach it to people who are kind of going through business calculus. So that way they can kind of see what it looks like before they go into something that might be a little bit more complicated. And it's a good introduction to some of the higher level kind of differentiation that you can do. So if you're ever going into multivariable calculus, you'll be prepared for that. All right, and if we want to look at a second example, we can look at the case of a circle with a radius of r. And so the definition of that circle would be y squared plus x squared equals r squared. And r would just be a constant. And so if r is a constant and we do implicit differentiation, well, you say that y is a variable of x, then we end up with dy squared, where y squared is just a term being differentiated by dx. Then we would add x squared dx, where x squared is just a term and we're differentiating it. And then we would set it equal to the derivative of r squared, where r squared is just one term. It's being differentiated with respect to x again. And so this is the way that we would do implicit differentiation for this relation, where we're just differentiating each of the individual terms and seeing what we would get out. For the r squared, the differentiation with regards to x just makes that constant go to 0, because r has no relation to the change in x. So as x on the circle, the x coordinate on the circle would be changing. There's no change with regards to what r is. R is always constant for whatever circle we've got and we're looking at. So this r squared would never change in any of those cases for a particular circle. And so that is always going to be a 0. So that's a conceptual way to think of what that derivative ends up being. If we are looking at the first couple of terms here, which are the actual definition of the circle, the relation between the variables, we can take a look at dy squared over dx. And if we do that derivative, we end up with 2y y prime. And so this y prime here comes out because y is not this x term. This is a function of x. And so we're really doing a chain rule here, where we're doing this squared term of some function of x. And so since we're doing this sort of a chain rule here, we have to take both the derivative of that squared term, which is 2y, and then also take the derivative of y and multiply the whole thing by it. And so that's where this extra y prime kind of comes from, is that idea of taking the squared operation as well as the extra derivative of what was the function on the inside. And so that's why we have this 2y y prime as our first term after doing differentiation with respect to x of y squared. Now, if we look at x squared and we do differentiation with respect to x, we're going to get 2x. So x, if we're doing the derivative with respect to x, we just do it like we normally would, like we would think of doing it if it was just a normal function. And so we end up with just power rule with regards to 2, where we would roll down the 2 and then subtract 1 from the 2 to get an exponent of 1. And so we have the 2 out front, x with an exponent of 1, which is just x. And then that's going to be what our whole term is. And so we found the 0, we found the 2y y prime, and we found the 2x. And so now we can say this is the equation. And since we have this equation, what we can do is we can reduce it, or we can solve for the y prime again and isolate all the terms that have y prime on one side, and then move all the other terms to the other side. And since there's 0 minus 2x, we end up with negative 2x on one side. And what we'll do is we'll end up dividing by 2y, so that way we can isolate y prime by itself. And if we're able to isolate this y prime by itself by dividing by 2y, we end up getting y prime equals negative x over y. And so this is what we'll have for our relation for the derivative of y, or derivative of a tangent line of our circle. And so we'll be able to know what the slope would be for any particular tangent line that would be on the circle. And so that's kind of what this represents. If we look at a particular example where we have the point 3, 4, then we can plug in to our function that we found implicitly for the derivative. We can plug those variables of 3 and 4 in to get y prime equals negative 3 over 4. And if we look at where the point would be on the circle for 3, 4, where we would go over 3 and then up 4, this would be the point on the circle. And if we were going to look at the tangent line would be decreasing, and it would be decreasing at a value which is less than 1, which fits with what we got for the slope of a tangent line from our implicit differentiation, which is negative 3/4. And so you can kind of see that the idea of that tangent line slope kind of matches with what we've got for that derivative that we found implicitly or through implicit differentiation. And so that's an idea that you kind of take with you to any sort of function modeling that you might be doing in multiple variables. And so if you're looking at things that have multiple variables, this can be useful. For a majority of what we're going to be doing, I think we'll mostly be sticking with explicit differentiation. But this topic is useful for things that might be more complicated than just looking at one variable at a time. Businesses often operate with multiple different variables with regards to how they're producing something. It usually takes more than one thing to produce something, whether it be energy or resources, manpower. There's a lot of things that go into production or services and goods. And so businesses in general will use multiple variables in order to solve for optimizing different things. And this can kind of help, this idea of implicit differentiation can help with some of those more complicated situations once you get to them. So it's good to see before you get there. And this is just a little introduction for that. So, all right, I hope that you guys enjoyed this, and I'll see you guys next time.